There you go. All right. I think it's recording, right? Yeah. So we were talking about homogeneous transformation. Remember, we introduced that T matrix, which basically was transformation matrix includes, which includes, is a transformation matrix includes the rotation matrix we talked about when we were talking about rotation kinematics. Includes the translation, the vector that basically should represent the translation of the origin of the body frame in global coordinate frame, and a bunch of zeros and ones. That was transformation matrix we introduced when we were talking about homogeneous transformation. Now, homogeneous transformation is like the value of homogeneous transformation becomes more apparent when we look into compound homogeneous transformation, meaning that you have multiple frames, and instead of just having one body frame and one global frame, and you want to transform the coordinates from body frame to global frame of coordinates of a point, now you have multiple frames, and your point, let's say the point you're interested in a specific frame, and you want to transform the coordinates of that point or that specific spot on the rigid body to not just one frame away, multiple frames away. And then that's where basically that's what falls into compound homogeneous transformation, right? So let's start that. Let me move a little bit. I can see you guys. There you go. So compound on this board I have a very bad handwriting. It's a different board from the one I have at home. Compound homogeneous transformation, or for short, just compound transformation. Now, if we have, let's say we have three coordinate frames, right? Let me draw it here. Let's say I have this one. I have some XYZ coordinates, and we can think about it as global coordinate frame, but here I'm going to use ABC. Since we have more than two frames, we want to talk about a situation that we're dealing with more than two frames. Let's call this X, Y, and Z, and let's say this is frame A. And let's go for the next one, and let's say we have another coordinate frame like this one here, CX, Y. Let's say this is, I'm going to call this X1, Y1, and let's say this is Z1. And let's call this frame B. And also, let's say now we have the third one. It's compound, so we have more than two frames. Let's put it here. X, Y, and Z. I can probably do a little better than that. X, Y, Z. I just want to show that they can be in any direction. So let's put this. There you go. And let's call this one X2, Y2, Z2. I call this frame C. So I have a couple of frames. Right now, instead of having G and B, global and body coordinate frame, now have frame A, frame B, and frame C. And let's also go with some good naming there. Let's say this translation from here to here. We can call this, let me get the notations right, D1 in A, and let's call this from here to here. We'll do a little better. Here to here as D2B, and eventually the one that is from, there you go, position of the third frame in the original frame. I don't know where that comes from. Let's call this D2 position of the origin of frame 2 in A. All right, so the way I named them, I said D1A, meaning that where the frame X, Y, 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 Z, Y, or frame B is in frame A. D2B trying to say that where frame C is in coordinates of the origin of frame C, represented by X2, Y2, Z2, in frame B, represented by X1, Y1, Z1. And the coordinates of the origin of frame C, represented by X2, Y2, Z2, in frame A, represented with D2A. And these are origins, so you can think about this as O1, think about this as uppercase O, and think about the other one as O2, right? Now, what we want to do is that we want to find out how can we transform coordinates from C to A, for instance, right? Before we only had two frames. We were going from C to B or from B to A. Now we say, well, I want to go from C to A directly. Now, how can I transform coordinates? And that's basically what compound transformation is, right? Multiple transformation instead of just one. Now, if you write it, let's say transformation from let's say from B to A, right, transforming coordinates from frame B to frame A, from B to A, I can represent that using transformation matrix from B to A. Right? And remember this one, that's very ugly. I cannot draw a straight line apparently. Let me use a tool. All right. So this one, we said, well, transformation matrix has 4 components. The important ones, rotation matrix 3 by 3. Then we have the translation D and zeros and one. So this becomes R, rotation of frame B in frame A, if you want to be very technical, put all the notations there. And then D1A, 0 and 1. Right? This was, we were separating these. And I said, hopefully you remember the whole story. And you did not forget what we were talking. So that's what I was doing back then. I said, well, basically transformation matrix is a rotation matrix. This is 3 by 3. This translation 3 by 1. This one is just 1 by 1, and this is just 1 by 3 by 1. Okay, 3 by 1. Let's just close this. There you go. So this is transformation, that basically transformation matrix that transforms coordinates from frame B to frame A. So if you have the coordinates of a point in frame B, using this, we can find the coordinate of that point in frame A. Right? This is not new. This is we know from before. Now, if we go one step forward and look at frame B and C, then the same story, we can write the transformation matrix that can transform coordinates from C to B, right? We can say transformation from C to B, TCB is, let me draw it this way. And my lesson, let me put the matrix first. There you go. This would be a rotation, right? From a rotation of frame C and frame B, and then D to B. Right? We're looking at frames B and C. Now you can think about frame B as global coordinate frame and C as body frame. Right? Previously, you could look at A as global coordinate frame and B as body frame. 0 and 1. Same story as before. Right? This is a 3 by 3 matrix. This is a 3 by 1 vector. This is just a 1 by 1, and this is 3 by 1. This is not 3 by 1. This is 1 by 3. Doesn't make dimensions. And same story here, 3 by 1. All right. So this is not new. This is what we had from before. Transformation from one frame to another. Now we are saying, though, if you have compound transformation, meaning multiple frames, I want to go to from one that is all the way at the beginning to the one that is all the way at the end, or you want to jump multiple frames instead of transforming coordinates of the points from frame C to B, find it in B, and then find the new coordinate you found in B, transform that from B to C. You can come up with a transformation matrix that basically transforms coordinates from C to A directly. And that's pretty straightforward. The transformation matrix that does that is a multiplication of transformation matrices that you had from before. So to go from, let's say, from C to A, right, so transformation matrix from C to A, right? So TAC is TAB, transformation from frame B to frame A, multiplied by transformation from frame C to frame B. So if you have 10 of these, if you think about that, you just multiply the transformation matrices, and then you get a transformation matrix, which is still a 4 by 4 matrix that can transform coordinates from one frame to a frame that is multiple frames away from this one. If I multiply that, or you can think about it this way: if you do the multiplication of this for 2 of them, if you want to get a sense of where things go, first row, first column gives you a 3 by 3 matrix, so this one becomes R from B to A, multiplied by R from C to B. Then you multiply that one, it becomes R from B to A. I don't know, where do I get C? From B to A, multiplied by D to B plus D1A. This becomes 0, and this becomes 1. So I just multiplied those two matrices in terms of matrices. Let's see what I did there. There you go. So basically what happens is that this, you can think about this as RAC, rotation from C to A. You can think about this one as a translation from this translation, whatever the origin of frame C is in frame A. Remember, this is what we have to. Yeah. This one is a 3 by 1. don't get lost there. This is a 3 by 1 matrix. This is a 3 by 3. This is a 3 by 1 vector, and this is a 3 by 1 vector. So the outcome of this is a 3 by 1, right? 3 by 3 multiplied by 3 by 1 gives you a 3 by 1 vector, plus another 3 by 1 vector. It gives you a 3 by 1 vector. And that would be the D2A, the value for that. And these two are two 3 by 3 matrices. It's this is what you have seen before, right? This is not new. This is multiple rotations. If you have your rotation matrix from frame C to B and rotation matrix from frame B to A, you just multiply them and it gives you successive rotations. We had this when we were talking about rotation kinematics.
I have a question, Professor.
Go ahead.
So we would do this in the case that we don't have the rotation matrix and the distance between A and C. You know what I mean?
We do so as opposed to what? As opposed to we want to find, the goal is to find the coordinate of a point in frame C in frame A.
Yeah. So the only reason why it's like 2 frames away is because we don't have the rotation matrix between A and C, is my question.
Yes, so when we start looking into robotic arms, you see that we attach frames to different, to each link. So if you have multiple links and you want to find out where the point is in this ground or global frame, and you know its coordinate in the frame that is multiple frames away from global coordinate frame, then you have to use this, right?
Okay.
Yes, in short, yes, because we can't go from A, well, we want to go from A to C. Now, there are 2 ways. Let's think about it this way. There are multiple ways of doing that. If you have a point, you can transform its coordinates from C to B first and find its coordinates in B. And then the new coordinates, you can transform those coordinates from B to A. So you can do this multiple times. Right? You can say R is equal to T R in global, or let's put it this way. You can say R in B is equal to T R in C, and then once you have R in B, you can say R in A is equal to T R in B. Right? You can do this multiple times, and as long as you know the transformation matrix from, if you have it from C to B and you have it from B to A, you can do this and take the point at C and do this multiple times and get to the coordinate in global coordinate frame, or frame A in this case. Right? Yeah. Now, what we're saying is that if you have this situation, multiple frame, instead of taking this point and doing it step by step, just find the compound homogeneous transformation matrix. And once you find that, once you know your T, then every point in the final frame, or the frame you have multiple frames away from your frame you're interested in to find the coordinates in it, just multiply those points with that transformation matrix. So if I want to write it in this way, I would say the value of this homogeneous transformation, we appreciate this more when we have several displacement occurring succession. Like you have 4 frames and you want to find the coordinate of a point that you know its coordinates in frame 4 or 5, and you want to find it in the global coordinate frame, the fixed frame. Let me write it this way. Clean this up. So I wanted to, let me wrap this up. So I wanted to say that this is equal to, that's equal to R C in A, rotation of frame, you can think about it this way, C in frame A, D A 2, 0, and 1. So it's the same thing as knowing how to go from A to C. Now, the value of this, let's actually put it as a note. The value of homogeneous transformation is better appreciated when several displacement occur in succession. What I'm trying to say is that I want to transform the coordinates of a point, let's say from frame 5 to global coordinate frame. Right? Usually when we deal with a robotic arm, we have a global coordinate frame that's fixed, doesn't move. And then we have frames attached to each link on this arm. So a point at the tip of the arm, we might know its coordinates in that frame, a frame attached to that link. But we want to find out what is the coordinate, because when we do path planning and we designing a path, how this, the tip of this arm, robot arm, how should this move from one point to another, we want everything typically in global coordinate frame, right? Because other frames, they're moving with respect to each other. Right? So if you think about that, it's going to be G1, then 1 to 2, 2 to 3, 3 to 4, 4 to 5. Let's look at a couple of examples. Maybe this start making a little more sense, right? But what are the situations that we're talking about here? That why do we even need to do compound homogeneous transformation, right? Let's go with do have a good example here. Let's go with something very general first. Nothing really before we get into nitty-gritty of playing around with numbers. Let me bring, I have it somewhere on my desktop. Hopefully it's this one. There you go. This is basically a, oops, not that. Good example there. This one is an arm that, if you remember, we were talking about revolute, prismatic, revolute joints and prismatic joint. We have a revolute joint rotating around this one. Right? This, let's think about this as a revolute joint. It's rotating. I don't know if I'm still there. We have a revolute joint. This is the axis of the joint Z. And we have the global coordinate frame, X, Y, Z. Right? It's fixed. Now we have another joint, right? A prismatic joint. If you see that, this is a prismatic joint. So this yellow link, we have rotation there, the gray part right here. On this one, we have a prismatic joint that basically elongates. Right? And then we have another revolute joint. This is a revolute joint. It's rotating around this axis Z2. So we have one revolute joint, first link. Then we have another link that is connected by to the next link by a prismatic joint. It elongates and it becomes long and short, basically one direction. Remember, we said in this course, any arm we represent or any motion we present, we use two joints: revolute joint and prismatic joint. And revolute joint pretty much was rotation, right? It had 1 degree of freedom. And then we had our prismatic joint. And we represent it, I think, pretty much using this. That was prismatic joint. We have for revolute joint, that was the axis of rotation or the joint axis. And for prismatic joint, this was the axis. So here we have an arm, simplified version. Right? There is a revolute joint, rotation. Then we have a prismatic joint. And then we have another revolute joint. Right? You can think about the first revolute joint, rotation around Z. The prismatic joint is translation along y1, goes back and forth. And the third joint is a revolute joint, rotation around z2. Right? So 3 joints. It's basically RPR. Revolute, prismatic, revolute. Orthogonal, and then the next one is also orthogonal. Now, let's see, in the general form, let's say we want to find the position. Let me clean this up. We want to find the position of this point P that is basically the tip of our, it's located at the tip of the last link. Now, typically, that's where your end effector gets connected. Let's say you have some pick and place arm. That's where your end effector is, and that end effector, let's say, is a gripper. It can pick something, move it somewhere else, and drop it there. Right. Now, we want to find the coordinate of that point P in global coordinate frame G. Why do we do this? Well, again, when we get closer to the end of the semester, when we start looking into path planning and how can we define the path for a specific motion. Let's say you want to define this path. You want this end effector to go from this point, I don't know, to this point maybe. We're defining some part of a path. When we do path planning, everything should be defined in a coordinate frame that is fixed. Because otherwise things are moving. You know, this prismatic joint is going back and forth, this revolute joint is rotating. So you know where this point is located, right? In this case, this point P, for instance. We know this is vector R, right? Going from the origin of B2 to point P. Represent the position of point P in frame B2. But what you typically want is that you want to find the position of point P in global coordinate frame G, because that's the one that's fixed. Everything else is moving. So in general form, let's just do a simple procedure, I guess. Let's say the position of P, that's at the end of this link, last link, in frame, it's called x2, y2, z2. So it's represented b2, x2, y2, z2 is r p in b2. Right? Just simple. This is r, this r we're talking about, right there. So we say this is r p in b2. Now we say frame, let me see, problem statement. Frame B2, describe the way this whole R moves. B2, X2, Y2, Z2 can rotate about Z2. So there's a rotation there. And slide along Y1. There's a prismatic joint right there, and it can slide in this way. And this. So the rotation around Z2, and you can slide along Y1. Frame B1, X1, Y1, Z1 can rotate. Clean this. Frame B1, right, represented by X1, Y1, Z1, right? That one can rotate about Z-axis, right? This axis right there can rotate about Z-axis, which is basically part of frame G. Z-axis of frame G. While its origin is at, while its origin, we can say its origin is at, so right there, is at D1G. There you go. Yeah, D1G. That's where the origin of X, Y, Y1, Y1, Z1 is. Now, what we want to do, we want to find the, let me get the following statement right. Find the expression. We are not really given that much information. We just want to represent it in general form. Expression for the position of P in frame G. Right? So we're pretty much describing what's going on there. X2, Y2, Z2 can rotate around Z2, that frame B2, and it can slide along Y1, X1, Y1, Z1. It can rotate, or frame B1, we have to say, it can rotate about Z axis of frame G, and its origin is located at D1. Let's represent this with D1G. Things are not confusing. And I'm going to do represent that one D2 B1. Can I do a better job? Let's see. D2 B1. So I'm going to stick to the notations that we've been using. All right. So a lot of talk there, but what is this? What this example is trying to do is that to show you the general procedure. There is not really that much information about X, Y, Z coordinates. All is trying to say that, well, if you have T, right, you want to find the transformation, right? You want to find the expression for point P in global coordinate frame. So you want to find where this point is in frame G. Now, you have frame B2, you know its coordinate of point P in B2. Then you have B1 between B2 and G. So you have to do compound transformation, right? Go from B2, which you know is the coordinates in that frame, to G. So T, B2 to G, right? Which basically means you have to go from T, B1 to G, and T, B2, T1, a successive transformation. Once you find this transformation matrix, any point that you know is coordinated from in frame B, you can find its coordinate using this transformation matrix. You can find its coordinate in frame G. Right, and this is straightforward. T B1 G again. This problem is not really looking into exact values. It's just asking you to come up with the general expression. So I can just write it as R B1G, right? And then D1G. I can separate these, it's too messy here. T, well, let's write it here. T B1G, right, would be your matrix there. This might seem like some kind of no-brainer problem, but I just want to give you a sense of what things, why are we even doing this compound transformation? Right? 0 and 1, right? And then you have T B2 B2 B1, which basically rotation between these two frames, and wherever the origin of frame B2 is in frame B1. There we go. So that will give you R, rotation matrix B2 to B1, right? This is going to be D, the coordinates, the position of the origin of B2 in B1. If it's, so that would be D, which we represented that with D2 B1. right? And then we have 0 and 1. So let me save that. Let's see if everyone followed what I did there. So again, let me not that one. We have the point P. Position of point P in frame B2 is given with RPB2. Now I want to convert these coordinates or position of P in B2 to position of P in G. You can think about it as this. I want to find this. R P RP in G, global coordinate. So what I need to do, I have to find a transformation matrix that can transform any coordinate from B2 to G. How do I do that? Well, that's compound transformation. TB2 from B2 to G is TB1 to G multiplied by TB2 to B1 transformation. Now TB1G is RB1G, like rotation of frame B1 in G, and then D1G. D1G is where the position of the origin of frame B1 is in frame G. And that's represented by D1G. Yeah, this is D1G. And this is the origin of frame B1. And D1G represent the position in frame G. Then DB2B1, transforming coordinates from B2 to B1, well, rotation from B2 to B1, and then the position of the origin of frame B2 in frame B1. Right? This is what we're looking at. This is the position of the origin right there. This is where the origin of B2 is. And D2B1 right there, D2B1, is the position vector representing the origin of frame B2 in frame B1. And the rest is just zeros and ones. So now we have transformation matrices. Multiply that, you get a transformation matrix that can transform coordinates from B2 to G. So T B2 to G. So if you multiply these, there you go, right there. And then or B2, so that becomes or B1G or B2 B1. Then you have or B1G D2 B1 plus D1G, and then you have 0 and 1 there. I'm just writing it in the general form. Obviously, this is a 4x4 matrix, the whole thing. Right. This is a 4x4 matrix. So this one gives you a 3x3 matrix. This one gives you a 3x1, and this is 1x1. This is 1x3. Then you can find, if you were given numbers, you basically can use this and find your coordinates. So R P in G is equal to T B2 in global coordinate frame times R P in B2. So once you know R P in B2, we're not given values here. And we can, once you know the transformation matrix, you can find any point, including point P, which you know is coordinate in frame B2, to frame G, which is your fixed frame. It's a simple example, but I don't know if it made things more confusing or more clear. So that's the story of compound transformation. Now let's look at I think let's look at it's better to look at something with more substance, I guess. These are just general representation. Let's look at something that we need to do multiplication and find the matrix. Let's bring, I do have this example that might be one step. There we go. So now we have this there. We have a simple two-link, as they call it, mechanism. I'll talk about links and I define them when we get to the next point. But for now, this is one bar, right? Let's say connected to another bar. And this one rotates around this point, and this one rotates around this point. This one right there. So we have two revolute joints. Right? There's a rotation. We are it's a planar motion. Everything is in an XY plane. So X naught and Y naught. This is your, let's say, B naught frame. X1 and Y1, this is your B1 frame. And X2 and Y2, this is your B2 frame. Now, let me clean it up. Now, and you have your rotations. This is rotating around this point, and this one is rotating around this point. Right? You can call this point O naught, I guess, if you want to call the origin O1, and this is the origin O2. Now, what we want to do is that we want to find the transformation matrix that can transform the coordinates from frame B2, the frame attached to the tip of this yellow link, yellow rigid body, to coordinate to coordinates in frame B naught. So we want to find a transformation matrix that can transform coordinates of any point in B2 to coordinates of the same point in B naught. Let's write it this way. Find the transformation, let's say, transformation from transformation matrix to transform coordinates from frame B2 represented by X2, Y2, Z2 to, let's say, coordinates in frame B naught, X naught, Y naught, Z naught. That's the coordinate transformation matrix or transformation matrix you want to find. Obviously, it's a homogeneous compound transformation matrix. Every transformation is homogeneous here. It's a compound transformation matrix, meaning that we have, right, it's multiple frames, and we're going to from, let's say, the B2 to B naught. So we have to do two transformations. So, same story. Transformation matrix that can transform coordinates from frame B2 to frame B naught is equal to transformation matrix that transforms coordinates from B1 to B0 multiplied by transformation matrix that can transform coordinates from B2 to B1. All right, now let's figure this one out. Let me just get rid of this. Oh, nothing. We're using it. So let's start with T B1 B0. All right, let's start with that one. T B1 B0. I'm finding these two separately, this one, and then I plug it in and do the multiplication. T from B1 to B0, well, let's just write it in general form. Rotation from B1 to B0, rotation matrix. Translation, I'll call that, let's just say D1, let's call it D1. 0 and 1. Maybe two are close. This is B1 and this is 1. So we have to find out the rotation matrix. What is the rotation matrix? Forget about everything else. Just look at B1 and B0. Right? Look at this part. Forget about B2 for now. Look at this frame right here. Look at this frame and this frame. Let me use different colors. This is B0, right? Let's call this B0. Now you look at these two. The rotation matrix. What is the rotation matrix B1 to B0? Which we know three rotation matrices, right? Rotation around X, rotation around Y, rotation around Z. These are only three rotation matrices we know when we were talking about rotation kinematics. Same story. This is a 3x3 matrix. This is a 3x1, 1x3, and 1x1. So what is that R rotation matrix? Forget about B1 and B0. You're looking at these two. Forget about the other part. Which rotation around which axis we can have here?
The z-axis?
Exactly. We only have rotation. We can only have rotation on z-axis. Like that's how the mechanism is moving. So this is rotation around z-axis. So I'll just put it here. Let me write it down. This is rotation around z-axis. So if you remember, it was cosine, minus sine, sine, cosine. And the angle is theta 1. This is theta 1 right there. We are looking at how does B1 rotates in B0. It rotates along about z-axis. This is Z0 here, like coming out of the screen. You can think about this as Z0, this way. B0 rotates around Z0, rotation around Z, and the rotation is theta 1. The angle is represented by theta 1. So this one becomes cosine theta 1 minus sine theta 1 sine theta 1 sine theta 1 cosine theta 1, and then we have 0 0 1 0 0. This is rotation, right? We are only looking at B0 and B0 and B1. These are all zeros, right? This is really nothing new. These are all zeros performing your transformation matrix. Now, what is D1? The coordinates of the origin of B1 in B naught coordinate frame. Right? Remember, this is the origin of B1. This is, you can think of it as O1. What is the coordinate? What was D1? D1 was representing the position of the origin of the second frame. You can think of it as body frame, in this case B1, in the original frame, B naught. So what is D1 here? I'm going to draw it here. This is X1, X naught, Y naught, coming out of the screen, Z naught. And then you have your X1, Y1. Right? This is your X1, this is your Y1. And you always had this as D. You had this as D. In this case, is D1, represented by D1. And this is your coming out of the screen, Z1. Right? This is what you had before. This is not something new. Don't think about rotation, kinematics, or transformation. This is your G now, if you want to think about it. This is your G now, and this is your B. Right? This we had before. Before we talked about compound transformation, when we just had the body frame and global coordinate. What is D1 now? Remember, D1 is a vector. Right? It has three components, X, Y, Z components. A vector that should represent where the origin of your B1 is in B naught coordinate frame.
Would the X be L1 cosine theta 1?
Exactly. L1 cosine theta 1, and the Y would be L1 sine theta 1. Right? And then Z is just 0. Thank you. So this becomes L1 cosine theta 1. This becomes L1 sine theta 1, 0 and 1. This is decomposing this vector. There we go. And here is this vector. The length is given as L1. So this one becomes, if this is theta 1, this one becomes L1 cosine theta 1, this one becomes L1 sine theta 1. Let me close this. All right. Let's do the next one. See if you got the idea. Let's do T B2 in B1. All right, then you're going to have your rotation matrix, right? The R B2 B1, right? Then you have your D, I'll call it D2, 0 and 1. If I was it there? Now here's what you have. Now you have again, this is the same idea of body frame and global coordinate frame, right? We are just going from one body to global to another body to global. We can always think about it this way. You can think about this one right now in this way. Now you have your X1 and Y1, and the next frame would be X2 and Y2. Right, let's put it this way. This would be your X1, Y1, You can think about this coming out of the screen as Z1. And this would be your X2, Y2, coming out of the screen Z2. Now, forget about B naught now. Just look at B1 and B2, right? If this is B2. Let's find the components. Now, rotation, right? If I draw this one here and connect these line to this one. This is, let me just write it as what we have there. This is L2. Now, what is the rotation matrix first? What is the rotation that, which rotation matrix first we have here? X, Y, or Z here? That's consistent. So we still have rotation around Z axis, right? These two, think about this one as B2 and think about this one as B1. Right? I'll not think of, they are B1 and B2. Now, how does B2 rotate in B1? Or how can we find B1? Any possible rotation is going to be around Z axis. This is your B1, this is your B2. Your B2 can rotate with angle θ2 with respect to B1. So your rotation of B2 with respect to B1 is a rotation about Z axis with θ2 angle amount.
So isn't it just the same cosine, negative sine, sine, cosine relationship with θ2?
Exactly. This is exactly the same thing, but with θ2. So this becomes cosine θ2 minus sine θ2 sine θ2. Sorry, go ahead. Cosine θ2 0, 0, 1, 0, 0. These are zeros. If this changes, there you go. What is the D vector, D2? Position of the origin of B2 in B1.
I feel like it would just be L2 cosine θ2 and L2 sine θ2,
Yes.
0, 1.
Exactly. So if you find the components of this vector, right, this L2 in your frame in global coordinate frame, remember, D, we write D in global coordinate frame. Think about this as global coordinate frame and this as local coordinate frame. It's exactly what we were doing before. We were writing D vector representing the origin of body frame in global coordinate frame. This is exactly the same thing as transformation. Now, in compound transformation, you just do it over and over. Every time you look at two axes, two coordinates, think about one of them as body and the other one as global coordinate. We just call it B0, B1, B2, B3, or any other letter that you want to use. So this one becomes, this is θ2. This one becomes L2 cosine θ2. And right there, this becomes L2 sine θ2. L2 sine θ2. So if I write it there, D becomes L1, L2. Where did I get L1? L2 cosine θ2. L2 sine θ2, 0, and pretty much 1. That's pretty much it. The 1 is always 1 then. Now you have transformation matrix from B1 to B0 and transformation matrix from B2 to B1. Right? If you want to find the transformation matrix from B2 to B0, you just have to multiply these two. Right? That's where we started. Right there. That's where we start. Right? Now, if you do the multiplication, that's fun. Right? Just two big matrices, you have to do multiplication. Multiply these two, first row, first column gives you the first element, first row of the first matrix multiplied by the second row. Just keep doing this. And you will get your matrix. Right? You will get something like this, a huge matrix as T from B2 to B0 becomes this one becomes cosine theta 1 cosine theta 2 minus sine, I'm going to write C and S, it's easier instead of comes a smaller C theta 1 C theta 2, means cosine theta 1 cosine theta 2 minus sine theta 1 sine theta 2. Next one becomes cosine theta 2 sine theta 1 minus cosine theta 1 sine theta 2. This is 0. This becomes L1 cosine theta 1 plus L2 cosine theta 1 cosine theta 2 minus L2 sine. I really got stuck there. Let me move things a little bit. Minus cosine theta 2 sine theta 1 minus cosine theta 1 sine theta 2. This is 0. Then it becomes L1 cosine theta 1. My L's are very weird in this course. Only in this course I write L for this. L1 cosine theta 1 plus L2 cosine theta 1 cosine theta 2 minus L2 sine theta 1 sine theta 2. Yeah, double check. Cosine theta 1 cosine theta 2 minus sine theta 1 sine theta 2 minus cosine theta 2 sine theta 1 minus cosine theta 1 sine theta 2. 0 L1 cosine theta 1 plus L2 cosine theta 2 cosine theta 1 cosine theta 2 minus L2 sine theta 1 sine theta 2. This becomes cosine theta 2 sine theta 1 plus cosine plus cosine theta 1 sine theta 2 cosine theta 1 cosine theta 2 minus sine theta 1 sine theta 2. This is 0. Then we have L2 cosine theta 1 sine theta 2 plus L2 sine theta 1 cosine theta 2 plus L1 sine theta 1. I'll check the last one. L2 cosine theta 1 sine theta 2 plus L2 sine theta 1 cosine theta 2 plus L1 sine theta 1. Right, this is 0, this is 0, this is 1. These are separate elements in the matrix. 0, 0, 1, 0, and then this is 0, 0, 0, 0, 0, 1. This is just basically a transformation from a simple two-link arm, right? If you want to transform coordinates from the tip, remember that's where we were looking at. You want to transform the coordinates from B2 to B0, this is going to be your transformation matrix. You can actually simplify this a little bit. If from math, I don't know how much you guys remember. I probably wouldn't have remembered if I wasn't really working with it. Review math. We know that sine theta 1 plus theta 2 is basically sine theta 1 cosine theta 2. Let me write it. Sine theta 1 plus theta 2 is sine theta 1 cosine theta 2 plus sine theta 2 cosine theta 1. This is a little bit of trigonometry there. Cosine theta 1 plus theta 2, depending on how much you work with it and how much you remember. Cosine theta 1, cosine theta 2, cosine theta 1, cosine theta 2, minus sine theta 1, sine theta 2. This is a little bit of math there. If you use this, for instance, this one, sine theta 1, cosine theta 2, sine theta 2, cosine theta 1. Let's go up there. Have to move things around a little bit. Sine theta 1, cosine theta 1. So the first one becomes, if I write this using that, let me write the matrix here. The first one, cosine theta 1, cosine theta 2, minus sine theta 1, sine theta 2. Sine theta 2 is the first element I'm looking at right there. That is this one, right? So you can write this as cosine theta 1 plus theta 2. The second one is minus cosine theta 2, sine theta 1. You just multiply sine theta 1 plus theta 2 by negative, and you'll get that. You will get minus sine theta 1 plus theta 2. Third one is 0. Right there, you can factor out L2. So that becomes L1 cosine. There's not that much you can do there. Theta 1 plus L2 cosine theta 1 plus theta 2. And if you factor out L2 there, right here, if you take L2 out, you get cosine theta 1 cosine theta 2 minus sine theta 1 sine theta 2. And that's basically nothing but cosine theta 1 plus theta 2. Same story, we can simplify the other ones. This one becomes sine theta 1 plus theta 2. The next one becomes cosine theta 1 plus theta 2. This is 0. This you'll get L1 if I factor that out. The first one, we can't really do that much about it. Sine theta 1. And then you factor L2 out. You'll get L2 sine theta 1 plus theta 2. And the rest is just 0, 0, 1, 0, and then 0, 0, 0, 1. Now, this is the transformation matrix that transforms the coordinates in a more simplified version. That transform the coordinates from frame B2 to frame B0. Now, this is just 2 links. Imagine what happens if you have 3 links, 4 links, if you have longer arms, and you want to find the coordinates of the tip in the global coordinate frame. This becomes much more complicated. You have to do the multiplication, you have to do simplification, and that's why when we start looking actually into arms in 3-dimensional space, we are going to use Mathematica to do a lot of this math for us. But the idea is not complicated. What we had from before, which was basically transformation matrix, now we have a compound one, meaning that instead of just a body and a global frame, now we have multiple frames, and we can go from one to another. We looked at examples of basically 3 frames, going from the third one to the first one, if you want to think about it that way. And we said, well, basically, you can just multiply your transformation matrices and get the general transformation matrix. Now, pay attention to rotation matrix. You know this from before, right? When you look at, when we talked about rotation kinematics, that's where we talked about rotation matrices, X and Y and Z. This is the same thing. D is what we talked about when we talked about transformation, right? Before compound transformation, we just talked about transformation, right? You know D from there. You should be comfortable with transformation matrix. Now, what happens in that in a compound one, you just repeat doing what you did for body and global, and just multiply them together. Okay. Yes, math becomes a little cumbersome, especially if it's a long arm with multiple frames. But the procedure should be straightforward. All right. We'll go over a couple more examples in next class. Question about this one.